Time delay relays, functionality and applications. Time delay relays are electrical devices used to control the timing of an electrical circuit. They are designed to introduce a delay between the activation of the relay and the operation of the connected load. These relays find applications in various industries and systems where timing is crucial, such as motor control, lighting control, HVAC, heating, ventilation, and air conditioning systems, and industrial automation. Here are some key aspects and features of time delay relays. The functionality of time delay relays revolves around controlling the timing of an electrical circuit. Here's a breakdown of their functionality. Control circuit activation. When the control circuit of the time delay relay receives a signal, typically in the form of an electrical current or voltage, it initiates the timing sequence. Delay period. Once activated, the time delay relay starts counting down a predetermined delay period. This delay period can be set according to the specific requirements of the application. Load activation/deactivation. After the delay period elapses, the time delay relay triggers the switching mechanism. This mechanism can either activate or deactivate the connected load, depending on the type of time delay relay and its configuration. Adjustability. Many time delay relays feature adjustable delay times, allowing users to finely tune the timing to suit their needs. This adjustability enables flexibility in various applications where precise timing is essential. Timing accuracy. Time delay relays are designed to provide accurate timing, ensuring reliable operation of the connected equipment or systems. The timing accuracy depends on the quality of the relay components and the precision of its timing mechanism. Repeatable operation. In applications requiring repetitive timing cycles, such as interval timing or recycling delay, time delay relays offer repeatable operation, reliably controlling the timing sequence each time the control circuit is activated. Compatibility. Time delay relays are compatible with a wide range of electrical loads, including motors, lights, solenoids, heaters, and other devices commonly found in industrial, commercial, and residential settings. Safety and protection. Some time delay relays incorporate safety features such as overload protection, short-circuit protection, and transient suppression to safeguard the relay, connected equipment, and personnel from electrical hazards. Overall, the functionality of time delay relays is centered around introducing a time delay between the activation of the control circuit and the operation of the load, providing precise timing control in various applications across different industries. Time delay relays come in various types, each serving different purposes in controlling the timing of electrical circuits. Here are the main types of delays associated with time delay relays. On delay, delay on make. In an on delay relay, the delay occurs before the relay contacts close and the connected load is energized. When the control input is triggered, there is a delay before the relay's contacts switch from their initial state, usually open, to their energized state, closed, activating the load. Off delay, delay on break. Off-delay relays introduce a delay between the deactivation of the control input and the switching off of the relay contacts, thereby de-energizing the load. After the control input is removed, there is a delay before the relay's contacts revert to their initial state, usually closed to open, deactivating the load. Interval delay. Interval delay relays provide a delay between the activation and deactivation of the load, with the relay contacts toggling between two states at regular intervals. Once the control input triggers the relay, there is a delay before the contacts switch to the energized state, e.g., closed, activating the load. After a predetermined interval, the contacts revert to their initial state, e.g., open, deactivating the load. Recycling delay. Recycling delay relays continuously cycle through a predetermined delay period, repeatedly activating and deactivating the load in a repetitive manner. After the control input triggers the relay, there is a delay before the contacts switch to the energized state, activating the load. Once the delay period elapses, the contacts revert to their initial state, deactivating the load, and the cycle repeats. These types of delays cater to different application requirements where precise timing control is necessary. For example, on-delay relays are commonly used for motor starting applications to prevent rapid cycling. Off-delay relays are useful in applications where a device needs to remain powered for a certain period after the control signal is removed, such as in conveyor systems. Interval delay relays find applications in sequential timing operations, such as traffic signal control. Recycling delay relays are used in cyclic processes where equipment needs to be repeatedly activated and deactivated at regular intervals, like in intermittent operation systems. Adjustability is a crucial feature of many time delay relays, allowing users to customize the timing parameters according to their specific application requirements. Here's how adjustability works in time delay relays. Delay time setting. Adjustable time delay relays typically feature controls or settings that allow users to adjust the delay period. This adjustment can often be made using potentiometers, switches, or digital interfaces, depending on the design of the relay. Precision control. Some time delay relays offer fine-tuning capabilities, allowing users to set the delay time with high precision. This precision control ensures that the timing matches the exact needs of the application, minimizing any potential errors or inaccuracies. Range of adjustment. Adjustability in time delay relays usually encompasses a wide range of delay times, spanning from fractions of a second to several hours or even days. This broad range enables the relays to accommodate diverse applications with varying timing requirements. Flexibility. The ability to adjust the delay time provides flexibility in adapting the relay to different operating conditions or scenarios. Users can easily modify the timing parameters to optimize performance, respond to changes in the environment, or accommodate evolving process requirements. Dynamic adjustment. In some advanced time delay relays, the delay time can be dynamically adjusted while the relay is in operation. This dynamic adjustability allows for real-time optimization or fine-tuning of the timing parameters based on feedback from the system or external factors. User interface. Time delay relays may feature user-friendly interfaces for adjusting the delay settings, such as intuitive knobs, buttons, or digital displays. Clear labeling and ergonomic design enhance usability and facilitate quick and hassle-free adjustment of the timing parameters. Locking mechanisms. To prevent unintentional changes to the delay settings, some time delay relays incorporate locking mechanisms or tamper-resistant features. These mechanisms ensure that once the delay time is set, it remains stable and secure during operation. Overall, adjustability in time delay relays empowers users to tailor the timing characteristics to meet the precise needs of their applications, enhancing versatility, performance, and efficiency in a wide range of industrial, commercial, and residential settings. Contact configurations in time delay relays determine how the relay interacts with the connected electrical circuit and load. Here are some common contact configurations found in time delay relays. Normally open, NO. In this configuration, the relay contacts are open when the relay is in its resting state, not energized. When the control signal activates the relay, the contacts close, completing the circuit and allowing current to flow to the connected load. Normally closed, NC. In the normally closed configuration, the relay contacts are closed when the relay is in its resting state. When the control signal triggers the relay, the contacts open, interrupting the circuit and preventing current flow to the connected load. Changeover, CO, or single pole, double throw, SPDT. This configuration features a common terminal connected to one of two other terminals, depending on the relay's state, energized or de-energized. When the relay is not energized, the common terminal is connected to the normally closed, NC, terminal. When the relay is energized, the common terminal is connected to the normally open, NO, terminal. This configuration allows the relay to switch between two different circuits or loads depending on its operating state. Double pole, double throw, DPDT. DPDT time delay relays have two sets of changeover contacts, allowing them to control two separate circuits or loads simultaneously. Each set of contacts operates independently based on the relay's state, providing increased versatility in controlling multiple loads or circuits. These contact configurations offer flexibility in how time delay relays interact with electrical circuits and loads, allowing them to fulfill various application requirements. Additionally, time delay relays may also feature auxiliary contacts for signaling or control purposes, further expanding their functionality and utility in control systems. Time delay relays find applications in a wide range of industries and systems where precise timing control is necessary. Here are some common applications. Motor control, preventing rapid cycling of motors to avoid wear and tear and extend motor life. Implementing soft start/stop operations to reduce mechanical stress and energy consumption. sequentially starting multiple motors to prevent overload conditions. Lighting control, delaying the switching on/off of lights for energy-saving purposes, such as in stairwells, corridors, or outdoor lighting. Implementing security lighting systems that activate lights after a delay in response to motion or other triggers. Controlling lighting in industrial facilities to coordinate with production schedules or occupancy patterns. HVAC, heating, ventilation, and air conditioning systems. Sequencing operations in heating, cooling, and ventilation systems to optimize energy efficiency and comfort. Delaying the activation of auxiliary equipment, such as fans or pumps, to prevent short cycling and improve system performance. Implementing time-based defrost cycles in refrigeration systems to remove ice buildup on coils. Industrial automation, timing operations in manufacturing processes, such as conveyor belt systems, material handling, and assembly lines. Controlling the timing of pneumatic or hydraulic actuators in machinery and equipment. Synchronizing the operation of multiple devices or processes in complex automated systems. Security and access control, delaying the unlocking of doors or gates in access control systems to verify credentials or allow time for security checks. Activating alarms or notifications after a delay to provide a window for disarming or responding to alerts. Pump control and water treatment, preventing rapid cycling of pumps to extend pump life and reduce energy consumption. Implementing time-based dosing or mixing processes in water treatment and chemical processing applications. Power distribution and protection. Introducing time delays in circuit protection systems, such as overload relays or motor starters, to allow for temporary overloads or inrush currents. Sequencing the startup/shutdown of power distribution equipment to prevent system instability or damage. These are just a few examples of the diverse applications of time delay relays. Their versatility, reliability, and precise timing control make them essential components in various industrial, commercial, and residential systems. Time delay relays can be categorized into two main types based on their underlying technology: solid-state and electromechanical. Here's a comparison between the two. Solid-state time delay relays. Technology. Solid-state relays use semiconductor devices such as transistors, thyristors, SCRs, or integrated circuits to perform switching and timing functions. No moving parts. Solid-state relays have no moving mechanical parts, which makes them more durable and reliable compared to electromechanical relays. They are less prone to wear and tear and have longer operational lifetimes. Fast switching. Solid-state relays typically offer faster switching speeds compared to electromechanical relays. They can switch on and off in microseconds or milliseconds, making them suitable for high-speed applications. Silent operation. Since there are no mechanical contacts, solid-state relays operate silently without generating noise or vibrations. Compact size. Solid-state relays are generally more compact and lightweight than electromechanical relays, making them suitable for applications with space constraints. No contact arcing. Solid-state relays do not suffer from contact arcing, which can cause degradation of contacts and produce electrical noise in electromechanical relays. Sensitive to overvoltage. Solid-state relays may be more susceptible to damage from overvoltage or voltage transients compared to electromechanical relays. Electromechanical time delay relays. Technology. Electromechanical relays use electromagnetic coils and mechanical contacts to perform switching functions. Proven technology. Electromechanical relays have been used for many decades and have a long track record of reliability and performance in various applications. Mechanical contacts. Electromechanical relays have physical contacts that open and close to control the flow of current. These contacts can experience wear over time, leading to reduced reliability and eventual failure. Slower switching speed. Electromechanical relays typically have slower switching speeds compared to solid-state relays, with switching times measured in milliseconds or longer. Audible operation. Electromechanical relays produce audible clicks when the contacts open or close, which can be desirable for some applications as an audible confirmation of operation. High voltage and current handling. Electromechanical relays are often capable of handling higher voltages and currents compared to solid-state relays, making them suitable for high-power applications. Contact arcing. Electromechanical relays can suffer from contact arcing, especially when switching high currents or inductive loads, which can lead to contact wear and degradation over time. In summary, the choice between solid-state and electromechanical time delay relays depends on factors such as switching speed, reliability, size constraints, environmental conditions, and specific application requirements. Solid-state relays offer fast, reliable, and silent operation with no mechanical wear, whereas electromechanical relays provide proven reliability and high power handling capability. Voltage and current ratings are essential specifications to consider when selecting a time delay relay, as they determine the compatibility and suitability of the relay for a particular application. Here's what you need to know about voltage and current ratings. Voltage rating. The voltage rating indicates the maximum voltage that the time delay relay can safely handle in the circuit. It's crucial to ensure that the relay's voltage rating matches or exceeds the voltage of the electrical system where it will be installed. Operating the relay above its rated voltage can lead to overheating, insulation breakdown, and potentially damaging the relay or other components in the circuit. Current rating. The current rating specifies the maximum current that the time delay relay can carry continuously without overheating or causing damage. It's important to choose a relay with a current rating that matches the expected load current in the circuit. Operating the relay at currents higher than its rated value can cause excessive heating, contact welding, or damage to the relay contacts. Inrush current. In some applications, particularly those involving motors, transformers, or capacitive loads, there may be inrush currents when the load is initially energized. Time delay relays should be capable of handling these inrush currents without experiencing damage or nuisance tripping. The relay's datasheet or specifications should indicate its ability to handle inrush currents and any derating factors that may apply. Inductive load rating. Inductive loads, such as motors and solenoids, can generate back EMF, electromotive force, when de-energized, which can cause arcing across relay contacts. Time delay relays intended for use with inductive loads should be rated accordingly to withstand the associated arcing and prevent premature contact wear or failure. Resistive load rating. Resistive loads, such as heaters and incandescent lights, typically have a steady-state current draw without significant inrush or back EMF. Time delay relays rated for resistive loads may have lower current ratings compared to relays intended for inductive loads, as they do not need to withstand the same arcing and transient conditions. Derating considerations. In certain operating conditions, such as high temperatures or altitude, the voltage and current carrying capabilities of the relay may need to be derated to ensure reliable operation. It's important to consult the relay's datasheet or manufacturer's guidelines for any derating factors that may apply in specific environmental or operating conditions. By carefully considering the voltage and current ratings of time delay relays and ensuring they align with the requirements of the application, you can ensure safe, reliable, and efficient operation of the electrical system. Time delay relays may incorporate various protective features to enhance the safety, reliability, and longevity of the relay itself and the connected electrical circuit. Here are some common protective features found in time delay relays. Overload protection. Overload protection mechanisms safeguard the relay and connected equipment from damage due to excessive current flow beyond the relay's rated capacity. Overload protection may include current limiting circuitry, thermal protection, or electronic overload detection to trip the relay and interrupt the circuit if an overload condition is detected. Short circuit protection. Short circuit protection prevents damage to the relay and connected components in the event of a short circuit where a low resistance path is created between conductors. Short circuit protection mechanisms may include fast-acting circuit breakers, fuses, or electronic current limiting devices to quickly disconnect the circuit and mitigate potential hazards. Transient suppression. Transient suppression circuits suppress voltage spikes or transients caused by sudden changes in the electrical circuit, such as switching operations or lightning strikes. Transient suppression components, such as surge suppressors, diodes, or metal oxide varistors, MOVs, absorb or divert transient energy away from the relay and connected equipment, protecting them from damage. Overvoltage protection. Overvoltage protection safeguards the relay and circuitry from voltage surges or spikes above the rated voltage, which can occur due to lightning strikes, power grid fluctuations, or switching events. Overvoltage protection devices, such as voltage clamping diodes or transient voltage suppressors, TVS, limit the voltage to a safe level, and prevent damage to sensitive components. Reverse polarity protection. Reverse polarity protection prevents damage to the relay and connected devices caused by incorrect polarity connections, where the positive and negative terminals are reversed. Reverse polarity protection circuits use diodes or polarity-sensitive components to block current flow in the event of reverse polarity, protecting the relay and circuit from potential damage. Thermal protection. Thermal protection mechanisms monitor the temperature of the relay and disconnect the circuit if the temperature exceeds a safe threshold, preventing overheating and thermal damage. Thermal protection may involve temperature sensors, bimetallic strips, or thermal shutdown circuits that interrupt the power supply to the relay until it cools down to a safe operating temperature. These protective features ensure the reliable and safe operation of time delay relays in various applications, minimizing the risk of damage to the relay, connected equipment, and personnel due to electrical faults, overloads, or transient events. When selecting a time delay relay, it's important to consider the specific protective features required for the intended application and environment. Overall, time delay relays are essential components in control systems where precise timing is required, providing flexibility and efficiency in various industrial and commercial applications.